Hello everybody, this is a presentation for the VQA workshop at CVPR 2021. I think we all agree here that VQA is a very exciting task, not only because it's very general, but also because it's very complex. We all know this example with the banana mustache from the VQA V2 dataset. And I think the complexity here really shines when you look for relevant training examples in the dataset. You can find examples about bananas and other about mustaches, but the complexity is really about combining those concepts and combining different reasoning mechanisms in ways that were not observed in the training distribution. So I would argue that VQA requires strong systematic and out-of-distribution generalization. The title of the talk asks whether we are building a ladder to the moon, and I think this is warranted because OOD generalization is mostly unsolved. If you look for papers on the topic, all you will find is mostly experiment on toy data like color depth. And why is this difficult? Well, that's because the empirical risk minimization principle that we use most of the time is basically about learning by association. So we learn basically any correlation that holds between the inputs and the labels in the training set. So we can make that more telling by looking at the simple example of image recognition. Let's say we want to train a bird detector. So first we collect some images, and in natural images, it's very likely that birds are going to appear in backgrounds of blue skies and tree branches. And the problem is that if we want to recognize birds in different scenes, like a bird in a parking lot, then this is probably not going to be as easy. And this is actually a test data from an OOD benchmark that's being used to test the robustness of ImageNet classifiers. So it's important to make a distinction here between the classical in-domain generalization and the strong out-of-domain generalization. The former is mostly about filling the gaps between the training examples. And I think it's generally agreed that there are some useful, almost universal inductive biases that can help here, some kind of smoothness prior. In this case, also more data almost always helps. Actually, in-domain generalization is solved with in the limit of infinite data. In out-of-domain generalization, it's very different. Here, it's mostly about distinguishing which features are robust ones and which ones are spuriously correlated with the labels. In this case, the bird shape is probably the robust feature, and everything about the background is mostly spurious. So here you need some additional knowledge that's usually task specific. To make that clear, let's say that with this data, the labeled bird was not actually bird, but was something like sunny day and tree branches. In this case, this label, so with the same data, just by renaming the label, you will realize that using the features of the background, so using the blue sky, relying on the blue sky and the tree branches, is actually the right thing to do. So that shows that with the same data, the task, that is how to generalize out of distribution, is not really specified by the data. And this shows that more data, more of the same data from this bias training distribution is not going to help. So the thesis of the talk is that to solve VQA and other complex tasks, this requires stepping beyond the framework of the classical statistical learning and learning by association. So in this talk, I will first review some principles from causal reasoning that I think are useful to think about what we can do beyond the framework of statistical learning. And then we will see some implications for the evaluation of models and then for the learning of better models. If you wonder why causality matters, remember that when we say that X causes Y, it only means that intervening on X affects Y. That is, setting X to a specific value has an effect on Y. And let's make that explicit with a simple task. Let's say we have images of car and we want to predict the top speed of the car. So let's say we collect some data that we annotate with the ground truth speed, and then we train a machine learning model on this data. So with a standard machine learning statistical model, you will learn correlations. And in this case, we have a lot of red Ferraris, and the model is probably going to learn that red means fast. And that's fine if the test data is also from the same distribution. But obviously, if we think a little bit about this task, we know that there's no causal relationship between the color and the speed. So the idea of a causal model is that we encode the effect of interventions. That is, what would happen to, say, this blue car if we were to repaint it. Obviously, it wouldn't get any faster. And so with such a model, we can make predictions in conditions that were not observed in the training data. That is essentially out of distribution. So the difference between those two models is that we learn very different mathematical objects. And the important point to notice here is that getting more data, more of the same data, is not going to make the statistical model better. That is, getting more examples of red Ferraris is not going to help distinguish the fact that there's a spurious correlations between color and speed, but not a causal mechanism. So let's get back to VQA. I think the useful view here is to see two sides, the real world on one side and then the model that we learn on the other. So in the real world, we have a set of mechanisms that produce the observed data, the training data. And its causal structure matters because that's what defines which features are correlated and which ones are spurious or robust. And VQA, so what we call the data generating process, that's the set of mechanisms, that's basically a human annotator. So someone who takes an image and question as input and identifies relevant visual information and use that to produce an answer together with a question. In a learned model, we basically want to mimic this process. And the inference process, once the model is learned, also has a causal structure. So in the sense that it takes inputs and then produces answers. So we could draw the causal structure of what happens in a model, say a model that doesn't use the image at all, that goes directly from the question to the answer by using question biases. That's not desirable, obviously, but that can happen. Or we can have a VQ model that doesn't have an explicit attention mechanism. So the key thing here is that in the correct causal model of the real world, we have the model implies decomposition of the joint distribution into a set of mechanisms. And these mechanisms are mechanisms that transfer out of distribution. So those are robust mechanisms. That's the things that we want to learn. We don't care really about the, say, the marginal distribution of the images, but the mechanism that identifies the relevant visual features or from there goes to the correct answer. That's the bits that we want to learn and that are known to transfer OOD. If we can identify and basically factorize the joint distribution into those. So to learn a robust model, we basically want to identify and mirror some of the causal structure and mechanisms from the real world into the learned model. And so why is this hard? The answer is basically that we don't have the data. We don't have the information that's needed. So in a typical data set, we have ID training samples, which are basically samples from the joint distribution. And that is known to be insufficient to recover the causal structure of the data generating process. And so the fact is that we need something else. We need additional assumptions, or we need some task-specific knowledge. And this is something that we do sometimes, for example, with specific architecture, like designing attention models. And this is a way to basically inject some prior information about the causal structure in the model. So the key point is that with just a set of training examples, we don't have enough. We need to bring something else here. So we'll go back to the learning of models later, but first, let's talk about the implications of these principles for evaluating models. We want to know whether a model can answer arbitrary questions about novel, unusual scenes. We usually use a test set of examples that are from the same distribution as the training data. And this measures the in-distribution performance, but that's not sufficient. It's because the in-domain performance says nothing about the use of the model of, say, shortcut learning and other kind of biases. I think we've made a lot of progress in this area with test sets like VQA V2, VQA CP, GQA OD more recently, and also the use of counterfactual examples. And I will show you that all of these ideas can be formalized with causal principles very effectively. The useful concept here is the causal hierarchy proposed by Judy Appel. This hierarchy proposes three types of queries that we can make to a model. And so these queries are increasing difficulty. The first level is the association, and that's basically where we are kind of stuck with most of machine learning today. And the others, intervention and counterfactuals, these are the ones that are more relevant to causal reasoning. And I will show you that these three levels can be matched with different types of evaluation that we already do today. So the association is basically the classical test set with the same distribution as the training data, which, as we've seen, is pretty limited. The second level, the intervention, corresponds to the datasets like VQA-CP, where we have different distribution between the training and the test. And we can see that as actually intervening on some variables in the data generating process. And that's in this sense that this can be seen as an intervention. And then the last level, the level 3, can be matched with the pairs of counterfactual examples that have been proposed in a few recent papers. And so these examples are basically very similar questions and images, but there's a slight difference. So the difference could be either in the question or in the image. Most of the time it's being done with images. And the key thing is that we have a small difference across this pair that basically probes the model very close to the desired decision boundary. So usually the images have been edited such that the answer is flipped between the two images. So we can even imagine other scenarios where this counterfactual idea would be even harder. I don't think this has been done, but we could also, for example, ask a model to generate an alternative image for another plausible answer. So you would feed an image, question, and correct answer to the model, and then you could ask the model to generate an alternative image that could support a different answer than the one given. So the idea here is that we have three levels that are well defined and known to be harder and harder, and we have correspondence with some evaluation schemes. And so we can show with these principles that those evaluation schemes are better in the sense that they probe the model for better causal reasoning. Now let's see what are the implications of causal principles for the learning of better models. So let's stick with the causal hierarchy for one more slide. The key idea here is that a model that is capable of answering queries for a given level actually needs some information that is relevant to this level or a level above. So that means, well, it actually implies that the levels are indeed increasing in difficulty, strictly increasing, and also implies that we cannot learn to do some causal reasoning that is level 2 and level 3. We cannot do that only from observational data, that is the data from the level 1. And so this data, that's the data that we use most of the time. That's a data set of RID samples. And we know that this is not sufficient to build a model that's capable of level 2 and level 3. So you can see that intuitively as needing to have demonstrations of level 2 and level 3 to do level 2 and level 3 at this time. So if we have data from level 1, like I said, that's basically the standard data set of ID samples. So it just samples from the joint distribution. So then what does the data at level 2 and 3 look like? At level 2, that's the data that we would get after an active intervention, that is basically have an action on the world that modifies the training distribution. So for example, having data from different training, let's say, different annotation environments, or from a different, say, population of annotators. In the level 3, they will be getting data that's basically counterfactual data, in the sense that you would have pairs of examples that are minimally different but have a different answer. So just like the one we saw for that have been used for evaluation, if we can have this kind of data for training, then we get a better, well, we have different capabilities that were not possible with just the ID samples. Now I will show you that we can better understand and explain some successful techniques from the causal perspective. I will go through 3 existing techniques, and the first one is simply data augmentation. As you all know, this is about generating additional training examples by hard coding some transformations. And the causal view here is to formalize the data jointing process into something that looks like this. It shows that images are made from both spurious and reliable features. And those are both correlated with the labels because there is a hidden confounder that we note C here. And being a robust OOD here, that is relying only on the reliable features, that implies being robust against changes in the covariate C. And we know from what we've seen before that this cannot be done only from samples from the joint distribution over X and Y, but it could be done by observing some interventions on C, because this is bringing information at level 2. And data augmentation can be seen as actually doing some interventions, simulating interventions by basically editing the spurious factors that are encoded in S. Let's take, for example, the augmentation of images with geometric transformations. This is essentially intervening on the intrinsic parameters of the camera. Or we can say also that with VQA questions, if we augment them with rephrasings, that's basically intervening on the writing style of the annotators. So now we have samples from a modified distribution, that is the outcome of the intervention, and this is known to carry information about the causal mechanisms. So this is no surprise that this actually improves generalization. So what is this good for? I think interesting implications is that the root source of improvement here is that the root source of the improvement is in the specification of the invariances that are actually valid for the data jointing process of the task. So that means it is task specific. So there's no hope of finding universal augmentations in this sense. It has to be tailored to the data jointing process of the task. So you have to bring some information about the task, and it's something that we have some intuition for, but the causal perspective allows to formalize this. And the causal view has also been shown to be an effective way to design methods to select effective augmentations. And I invite you to have a look at the paper noted below here. Another technique that we proposed last year for VQA is unshuffling data. So this is basically recovering non-ID subsets of the training data. So this starts from the existing work that's been done in domain generalization, where the idea is that we have data collected in multiple conditions. Usually that's done for image classification, in which case we have examples of images from different domains like paintings, cartoons, sketches, and photographs. And our method shows that we can recover this kind of clusters in the data by choosing a good, using task knowledge basically to split the data into subsets that are relevant. So we need some task knowledge, so something that's very specific to, in this case, VQA, and also side annotations to basically condition the clustering on. But if you do that, so we did that for VQA CP and clustering on the question type and answer. So if you do that correctly, then you can actually simulate some interventions in the data drenching process, and that again brings information that we didn't have with the aggregated data. So we can formalize this again with the causal perspective. I will not go through the detail here. I will leave this to read later on if you're interested. But this really shows that we have information with this process that we did not have before with just the aggregated data set. And in this case, again, the root source of improvement is coming from the information that we put in the method, and that is task specific. So in this case, it's in the choosing of the clustering condition and the annotations, well, side annotations that we use to do this clustering. So nothing comes from free. It's basically the no free lunch theorem. And the last method I want to mention, it's the use of counterfactual training examples. So it's a paper that we had at ECCV last year that showed that we can get information from level 3 by using this kind of training data. So counterfactual examples, these are pairs of examples that are very similar but with a different label. So we can have this kind of data from annotators. In this case, these were movie reviews. So that's for a language task. Movie reviews that were edited. So we actually, well, the authors asked the annotators to specifically edit a given movie review to flip the label by doing just a few, well, minimal changes. But we can also get this kind of data by using task heuristics and side annotations, and doing some like in painting or masking regions that we know are relevant. In the case of VQA, we used data that was based on human attentions, and basically the regions on which the humans had a high attention. So that's basically the regions that were relevant for the question. Then we could mask those and remove the correct answer from the set of correct answers. So we can generate this data. And with these pairs, they were shown to be very good training data to learn a model that generalizes. And with the equal amounts of training data, this improved generalization much more than standard RID data. So this was prior work, and what we realized with the causal perspective is that the level 3 information is really in the relation across the pairs, not in the examples themselves. And so that motivated the design of a new loss, a loss that exploits the relation between the examples. So what we do is to compute a vector difference in feature space across a pair. And we use this vector difference to align the gradient of the classifier. So this is using some information that was there, but that was not used with the standard ERM type loss. And with this new loss here, we exploit some signal that was there but being unused. And so the causal perspective shows that we get information that we did not have before and that is relevant to generalization. And indeed, we get some pretty good improvements in generalization across datasets. So basically zero-shot transfer. And we showed that in VQA, but also in image tagging and some NLP tasks. Now some takeaways. The main message of this talk is really that there are some limits to what can be learned from a set of ID training examples. And it doesn't matter how many examples you have. So the causal perspective allows us to understand the limits of what can be learned from a given training condition. I think in this sense, causal reasoning is helpful, just like, say, information theory, in the sense that it sets hard limits on what you can do with some given resources. So the idea is that if you can learn something about the causal mechanisms and the causal structure of the world, then you can do much better. And the causal reasoning principles don't really tell you how to design better models or to learn better models, but at the very least, they can point you at directions on where to find the information that was missing before. I think the useful view here is to shift our focus from building better models, but rather think about building better training environments. That is, finding how to train models in a way that we can provide those missing signals that we don't have in the fixed training sets that we use nowadays. And so we saw some existing techniques that do this kind of thing by bringing some information that is of a different nature, by using different kind of data, using different kinds of annotations, sometimes annotations that are present in data sets but that are being unused. I think there's probably a lot more that can be done there. We have some sign annotations in some data sets, like the annotator identity, that could be used to, say, cluster the data into different subgroups. We could use also some data from non-stationary sources, in which case you have also changes in distribution over time that you could exploit. So there's a lot of ideas that I think are not exploited nowadays. And I think with this perspective, we could build models that have very different capabilities than what we are working on today. And the high-level view from what's been done and what's left to do, I think we can draw this parallel between machine learning and causal reasoning. So in machine learning, we've evolved from the good old-fashioned AI to deep learning, in the sense that we can now handle high-dimensional raw data with deep learning. And in classical causal inference, we have a lot of techniques that are suitable to discrete variables and predefined variables, like the kind of graph that I showed before. But this is obviously not suitable for the high-dimensional data like images and unstructured text that we want to use nowadays. So the next step is what some people have called causal representation learning, which is basically learning to discover latent causal variables and their structure jointly. And this should come both from ideas in deep learning and ideas in causal reasoning that both exist separately, but that need to be merged in some way. So I think there's a lot of exciting opportunities, and I hope I inspired you to pursue in this direction and make progress towards models that generalize better.